All right, so last time we started talking about imperfections in crystal structures. We said that there are no perfect crystals. There is no way to have a perfect crystal. There have to be some imperfections or defects. Some are good, some are bad. And we classify the defects based on whether it's point defects, line defects, or area defects. Area defects and line defects, we're going to talk about them inshallah ta'ala next class. Point defects, we said that it could be either one element. In case of one element, a single element, we can have a vacancy, or we can have self-interstitial, or we can have two or more elements. In that case, we have a substitutional and interstitial atoms. So going through just quickly that in one element we have vacancies and self-interstitials, and in the vacancies we said that there is a missing atom. In the self-interstitial we have an extra atom inserted, and we say that the vacancies are a must for all crystal structure. You have to have those vacancies, and it's much more common than the self-interstitial. And we have this equation to relate the number of defects or vacancies and the number of potential sites, activation energy, temperature, and the Boltzmann constants. Also, we solved an example about this equation in order to find out the number of vacancies in this case. Let's try to solve another example. I mean, just to reinforce the idea of utilizing this equation. So in this example, he's asking you to find the activation energy for vacancy formation in aluminum, given that the equilibrium number of vacancies at 500 C is 757 10 to the power 23 atoms per meter cube. The atomic weight, he's already given the atomic weight and the density in this case. So the first thing, as I said, just write down the equation NV over N equal exponential minus QV over KT. Do we have the temperature here, guys?
Yes.
Yes,
We have K, we have temperature, we have the number of vacancies. The only thing that we don't know is the number of potential sites and the QV, which is basically what he's asking. The N, we have done it before, Shabab, in the previous lecture. We say that the N is basically the rho NA over the A. You are not sure whether this one is correct or not. What you need to do is basically write the unit gram per centimeter cubed, atom per mole, and gram per mole. So this one will cancel out, this one will cancel out, we'll get atom per centimeter cubed, so everything is good. So just substitute the numbers here. So the rho, we have 2.62, and basically the Na 6.02 times 10 to the power 23 atom per mole. And finally, we have the atomic weight, which is 26.98. If you substitute and plug in these numbers into your calculator, then you will get the result of 5.85 times 10 to the power 22 atom per centimeter cube. Okay, so this is the number of potential sites. So we have now N. So how to get rid of the exponential here, guys?
Take ln.
Ln in both sides. So we have ln NV over N equal to minus QV over KT, meaning that QV is equal to minus KT ln NV over N, meaning that QV is equal to minus K, in this case is a constant, which is a Boltzmann constant. So it's basically 8.62 times 10 to the power minus 5 electron volt atom per Kelvin. temperature, should we use 500 or 773, guys, here?
773.
Why?
Because the units are in Kelvin.
Exactly. So 773 Kelvin. And then we basically Len in V is 757 times 10 to the power 23 atom 23, and we have the N is 585 times 10 to the power 22. Did I make a mistake here, guys? Is there something wrong? Does it make sense? Look at the NV over N. Does it make sense? Is it possible to have the number of vacancies greater than the number of potential sites? So we have more vacancies than we have atoms, basically. Is it possible?
No.
No.
So what is the mistake that we have done here?
The number of vacancies is wrong.
The number of vacancies is what? Again, I cannot hear you. So what did we do wrong here, guys? Or we forgot to do, basically?
We should reverse the fraction.
Reverse what?
The fraction.
No, we shouldn't. So the only thing that we have done wrong here, look at the units, ya shabab. And that's why I tell you always write down the units, okay? So you see the unit of vacancies is basically atom per meter cube. But what did you do here?
Per centimeter.
Exactly. So I'm telling you this, maybe it sounds silly, but believe me, many students get it wrong in the exams, okay? So just keep track on the units. Very important, shabab, okay? So we have to convert it. So this will be 28 atom per meter cube. Now it makes sense. We have more atoms than vacancies. So basically now if you plug in these numbers into your calculator, you'll find out the result to be 0.75 electron volt per atom. Okay. So then we talked about having two or more elements. Then we said that there are two outcomes. One is to have, if you add B into A, you can have a solid solution, because basically we have random distribution of points B in A, between B and A, and the B can basically exist as a substitutional solid solution, meaning that if you add B, you will basically substitute A with B. In that case, we like a copper and nickel. Or we can have something like called interstitial solid solution, meaning that the atom B is very small, that it does not substitute, but it goes inside within the void, within the unit cell itself. So this is outcome number one. Outcome number two, we can have a solid solution of B and A. And also we can have a new phase formation, okay? Like this example, we have solid solution in this region here. And in this region here, we have basically new phase formation, and that new phase formation usually have different crystal structure and different properties. Okay. So also we talked about the conditions for substitution of solid solution, and those conditions we apply something called the Helmholtz-Rotary rule. And the Helmholtz rule, basically we have delta R less than 15%. When I say less than 15%, meaning delta R can be minus 15% or 15%. So it's within 15% range. Proximity to the periodic table, same electronegativity meaning, and same crystal structure. These we have talked about in the last lecture. And the valency if all of things are equal, so it's greater tendency to basically dissolve metal with higher valency than the lower valency. So let's try to apply these rules into this equation, and let's focus on the copper. And here I'm gonna give you examples, but in the homework you will see much more examples than this. Okay? So in the copper, for example, if you look at the copper here, we can have either of three situations. We have complete solubility, we have incomplete solubility, or we can have something interstitial. Solid solution. So in the homework, you're gonna check every element, but I'm just gonna give you example. It's just I'm gonna check nickel, for example, here. So we need to determine whether nickel will be complete solubility, incomplete solubility, or interstitial. So the atomic radius of copper is 0.1278. The nickel is 0.1246. If you calculate delta R, in this case, it will be -3%. So it satisfies rule number 1. And then proximity to the periodic table, similar electronegativity. Here we have 1.9, here we have 1.8, so it checks number 2. Same crystal structure of pure metals. So here we have FCC, here we have FCC, so it checks number 3. The valency, so here we have +2, here we have +2, so it checks number 4. So in that case, so we say nickel has a complete solubility in copper. So no matter how much you add nickel to the copper, you will form a solid solution. You will not form any other phases. So this is situation number 1. Situation number 2 is an example of silver. So let's look at the silver. So here is 1.278, here 0.1445. If you calculate delta R, it will be 13%. So it checks number 1. Proximity, here we have 1.9, here we have 1.9, it checks number 2. Same crystal structure, here we have FCC, here we have FCC, so it checks number 3. Valency, here we have +1, here we have +2, so it does not check number 4, so that's why we said the silver is basically incomplete solubility. So we can add the silver until a point and then we'll form another phase. So if you have different valency and or different crystal structure and or different electronegativities and or delta R is greater than 15%, you will have incomplete solubility. And finally is the interstitial. We can take an example of carbon. Carbon, you see, is very small in size. So if you calculate delta R, it will be -44%. So it's very small compared to the copper. So in that case, the carbon is more likely to go into the interstitial sites. طيب أي سؤال يا شباب؟
Doctor.
تفضل.
And the electronegativity, what is considered similar, what is considered ancillary?
Okay, that's really a good question. Okay, so I would say, okay, there is even though there is no fixed rule for it as far as I'm concerned, but if it is within plus or minus 0.2, I would consider it similar connectivity. Okay.
Okay, clear.
Even though that rule is not clear, and I had the same question. Okay. طيب.
دكتور.
تفضل.
Some elements have has multiple valence numbers. What about them?
Okay, that's
Like,
good. So we can have elements with different valence number. Also, we can have elements basically with different crystal structures. صح ولا لا? We've talked about allotropy. For example, here, if you consider, let's say, iron, This is a very interesting choice, okay? Iron has a BCC, okay? But if you heat it, it will transform into what, Shabab?
FCC.
Exactly. So if you heat it above 912, it will turn to FCC. So we can say that at high temperature, iron will have complete solubility, but at low temperature, it will have incomplete solubility. So it's true that some elements have different valence, but what we are concerned is basically at that valence, okay, if that element has this valence, will have solubility or not. Similar to the structure, okay? We are concerned not about the elements in general, no, about the exact structure at this temperature. So here also we are concerned about the exact valence for this element, whether it will have complete solubility or not. I'm not sure if I answered the question or I added some confusion to the answer.
No,
Does it make
it's
sense?
clear, but which valence number will I have to take?
Okay, so usually to be given, okay?
Okay,
So the case will be given.
thank you.
No problem. Bye. So this is for the substitutional. Interstitial, as we said, it has to be very small. So we know that the metals have high atomic packing factor. Interstitial elements must have very small size, so they can occupy the voids, typically below 10%. If you see the steel, Shabab, it's made of iron and carbon mainly. And the carbon is the maximum is less than 3%, okay? Maximum. And usually it's below 1% or 2, below 1%, but maximum is below 3%, different type of steel. So typically it's below 10%, so not more 10%. So this is something to keep in mind. Okay, so, and they can occupy the voids, and they have specific places. Forget about these dots for a moment. What is the crystal structure of this unit cell, Shabab? Is it FCC, BCC, simple cubic?
FCC.
FCC, okay?
FCC.
Yeah, that's simple cubic. So the interstitial atoms can occupy either in something called octahedral site or tetrahedral site. Octahedral site meaning that we have a coordination number of 6, meaning that there are 6 neighboring atoms, like you see 1, 2, 3, 4, 5, 6. And this is the same thing. We have 1, 2, 3, 4, 5, and 6. So this is the octahedral site. Tetrahedral site is 4. So basically we are talking about only 1, 2, 3, 4. So this is called the tetrahedral site. So coordination number is 4 for tetrahedral sites. So these are different sites where basically the material will occupy these positions. The interstitial atoms. The similar thing we can do it for BCC. We can have octahedral site. We have 1, 2, 3, 4, 5, 6. Because we have another atom here, we have another atom here, we have another atom here, parallel to this one here. Also, we have tetrahedral site. Tetrahedral site is location is 1, half, 4. So we are talking about 1, 2, 3, and the one in this side, basically 4. So this is basically the positions for the tetrahedral site. Now, why do you need to do this? Because if you take advanced courses or you're taking, inshallah, you're gonna be dealing with some XRD or some ceramic materials, the location of these is very important. And you will hear a lot octahedral site, tetrahedral site when we're talking about impurities. Let's try to solve an example and apply this knowledge here. For example, he's saying that compute the radius R for an impurity atom. So we have R for impurity atom. fits into BCC octahedral site. So this is the BCC octahedral site. In terms of atomic radius R of the host atom, so R, capital R, is the host atom in this case, without introducing a strain. So if you look at this exactly line, it will be something like this. So here, there's no impurity atom. So basically, this is typically what it looks like. And here we are adding impurity atom. So he's asking that how much the radius of small r in terms of capital R that we can insert inside without causing any stress, meaning that the maximum radius of this impurity atom. So we know from previously that this is A, the edge length. And A for the BCC, do you remember, Shabab, what is the A for the BCC in terms of R? There's a relationship between A and R for a BCC.
Root 3. 4
over square.
Yeah, 4 over square root of 3. This is the relationship. So this is relationship number 1. Relationship number 2, that if you look at the A, which is the same thing as here, we are talking about A is equal to R plus 2 small r plus R, meaning that 2 capital R plus 2 small r. And this is relationship number 2. So we can equate both of them, and we will have 2r plus 2 small r is equal to 4 over square root of 3 r. Now we can shift everything to the other side. You will end up with the small r is equal to 4, or let's say 2 over square root of 3 r minus r, meaning that r is equal to 2 over square root of 3 minus 1 r, or we can say that the r is equal to 0.155 r. So this is the maximum radius of the host of the impurity atom that we can add in this position in order to not cause any stresses. You see, it's only 15% of the size of the host atom. Any question, Shahab? Good. So we have talked about the point defects, vacancy atoms, self-interstitial, interstitial atoms, and substitutional atoms. The only thing that we need to talk is basically how to explain when we have 2 or more elements, meaning that you have atom A and atom B. Now we have a solid solution. Now, how to express the composition, for example, of atom A in that solid solution? So we have 2 ways to do that. We have in terms of the weight percentage, meaning that the mass of one component divided by the total mass, easy, or the atomic percentage, meaning that the number of moles of one component divided by the total number of moles. So far, so good. So we can do this, and this is, we term it as C1, and this is C1 prime. We can do this for sure, and we can basically write C1 in terms of C2, or C1 prime in terms of C1. For example, if you look at the C1 prime here, C1 prime is equal to N1 over N1 plus N2 times 100. And we know that the N is equal to the mass over the atomic weight. So basically M1 A1, M1 A1 plus M2 A2 times 100. And we can unify the denominator here. we will have M1A1, M1A2 plus M2A1 divided by A1 times A2. We can get rid of A1 here and move A2 here. You will end up with the M1A2 divided by M1A2 plus M2A1 times 100. So in order to convert it into C1, then we multiply both with M1 plus M2, M1 plus M2. We can do this. So we will have M1 plus M2 times E2, M1 plus M2, A2 plus M2, M1 plus M2, A1 times 100. Now this one, M1 over total mass, is basically C1. So in that case, we write it as C1, A2, C1, A2 plus C2, A1 times 100, which is the same as this one here. So you can of course do this. So this is the reason for this one, but you can do this as well. You can do this as well by doing the same derivation here. Or sometimes we are interested to find the mass of one component divided by the volume of material, meaning that, for example, C1 double prime is basically, you can start from M1 divided by V1 plus V2. And from there, you can basically apply the one that we did and apply the similar to the thing that we have done in the previous slide to find out the relationship. It will be equal to this one. Or sometimes we need to find the average density. We know that density is equal to mass over volume, meaning that the average density you can start from M1 plus M2 over V1 plus V2. And from there, you can substitute the value for the V1, M1, M2, etc. Or sometimes we need to find the average atomic weight. In that case, average is basically M1 plus M2 divided by N1 plus N2. And you can basically apply the equations again to find the average atomic weight. We're going to solve an example about derivation in a minute. But these are basically specification of composition, meaning that you have a composition, you need to find the atomic percentage of one component, or the weight percentage, or the average density, or the average atomic weight, or basically the mass with respect to the volume of the whole material. So these kind of things is helpful when you are talking about a solid solution system. Okay. So here's an example. He said that what is the composition and atomic percentage of an alloy contains 45.2 kilogram, 46.3 kilogram of zinc, and 0.95 kilogram of lead. So the way to do it is, we know that C copper, for example, is equal to N copper over N copper plus N zinc plus N lead times 100. And we know that the N is basically the mass over atomic weight. So mass of copper, atomic weight of copper. And here basically we have mass of copper, atomic weight of copper, plus the mass of zinc over atomic weight of zinc, plus the mass of lead, atomic weight of lead, times 100. So we have the masses, the atomic weight will be given, but just be careful. Usually the atomic weight is in gram per mole, is given, and here is in kilogram. So you have to convert, okay? So here you see he multiplied by 1000 to convert it to gram, and then he divide by the atomic weight to find the number of moles, and from the number of moles he substitute into this equation here to find is 50 atomic weight percentage, and the zinc is 49.7 atomic weight percentage, and the lead is 0.3. Or we don't have to do this actually for lead. We can basically do is 100 minus 50 minus 49.7. You will end up with the result of 0.3 atomic percent. Okay, شباب. طيب. Here's an example. He said that he wants you to find or determine or develop an expression like this, which is basically the number of atom per cubic centimeter of element N1. So he said that N1 is basically the number of atoms by the total volume. So we're talking about V1 plus V2. So the number of atoms is equal to Na times N1, which is the number of moles. And also this one is equal to Na times the mass over the atomic weight. So we can substitute in this case N1 is equal to M1A1 times Na. Okay. And the V is basically mass over rho density. So we can say that the mass M1 over rho 1 plus M2 over rho 2. So we can basically put this one here down. So by basically multiplying A1 over A1. So N1 is equal to M1 Na M1 A1 over rho 1 plus M2 A1 over rho 2. And then what we can do is to basically multiply by M1, M2, like what we have done before. You will end up with the result of N1 is equal to C1 Na, C1 A1 over rho 1 plus C2 A1 over rho 2. And we know that the C1 plus C2 is equal to 100. So N1 is equal to C1 Na, C1 A1 over rho 1, and here plus A1 over rho 2, 100 minus C1. If you are into math, you might like these derivations. I mean, you can derive also the previous equations. If you are not like math, you have to endure it. Any questions, Shabab? So far we basically we are done with the point defects. We have talked about the vacancy atoms, self-interstitial, interstitial atom, and substitutional atoms, and the specification of compositions. Next class, inshallah, we're going to conclude chapter 6 by talking about the line defects and the grain bound, the line defects and the area defects, inshallah ta'ala. طيب أي سؤال؟